Morphin time! Dragonzord!
Mastodon!
Pterodactyl!
Triceratops!
Saber-tooth tiger!
Tyrannosaurus!
Yeah!
We're back! We're ready to morph into action! 6 working together to fight evil!
And stop Rita and all her menacing monsters!
From destroying our planet Earth! And ruling the universe with evil!
Look out, Rita! We're not backing down! We're the Power Rangers! Look! They're coming together!
Go, go, Power Rangers! Go, go, Power Rangers! Go, go, Power Rangers! Fighting for Power Rangers!
Rangers, I give you Dragonzord in fighting mode.
Go, Power Rangers!
Check it out! Man, it's more phenomenal!
Hi everyone, in this CSE 373 review video, we're going to be talking about Mergesort, which is a sorting algorithm that uses a divide and conquer strategy. All sorting algorithms that use this strategy have 3 main steps. First, their input is divided into multiple pieces, then each piece is sorted recursively, and then each piece is combined to get a fully sorted final product. So let's start with this array as an example here. We're going to first divide the array into 2 parts for merge sort. Then we're going to recursively sort each part into a fully sorted piece. And then we're going to combine these pieces into a final fully sorted array. So let's look at the divide process in a little more depth. We have one of our initial pieces here. And what we're going to do is we're going to recursively divide this piece into 2 pieces and then divide each piece into 2 other pieces and do this until we have our base case, which is a 1-element array. And we're going to have 5 1-element arrays because there are 5 elements in the starting array. All right, so now let's talk about combining these 1-element arrays. So we're going to combine each element and we're going to try and maintain our sorted order. So what I mean by that is if we combine 8 and 9, those are already in sorted order, so we're just going to leave them. 0 and 2 are also in sorted order, so we would just combine them. But if they weren't, we would add them in the reverse direction. So we add 8 and 9 and 0 and 2 into these 2-element arrays. And then we combine these 2-element arrays into one 4-element array, again maintaining the sorted order. And how we do this is we look at each element and add the lowest one for each pair into our new array. And we'll get into this a little more in detail later, but then we have a sorted combination of those 2 arrays. And finally, we add our leftover 1-element array here into a fully sorted 5-element array. I just noticed a mistake while I was editing. In the previous slide, the 5 doesn't actually add at the end. It's going to add in like the same order in which it was split. So it's going to add to a 2 long array to make a 3 long array and then eventually add to the final product. Sorry about that. Okay, so now we have our recursively sorted pieces and we're going to add them together and maintain our sorted property into a large final sorted array. So how do we do this? Well, we're going to be comparing elements and adding the lower element or the less element into our full final array. One thing to keep in mind as well is this is actually how all combine operations work in Mergesort. I'm just showing this last final combine operation as an example. So we want to compare 0 and 1, and 0 is less, so we add that to our array, and then we increment our pointer by 1 space. 1 is less than 2, so we add that into our array. 2 is less than 3, so we add that, and we're incrementing every time. And we're just going to continue until we've added everything in this right-hand array. So now we're just going to add the rest of the items in the left-hand array. Perfect. And now we have a fully sorted array that we use Mergesort to sort. So there are also a couple factors we want to discuss when talking about sorting algorithms. And one is whether that sorting algorithm is in place, which means it only takes O of 1 space complexity, extra space complexity. And the other is whether the sorting algorithm is stable, which is whether equal elements stay in relative position after being sorted. So for Mergesort, this is not an in-place sorting algorithm. At least the one we've discussed, you see that we're making tons of different arrays and we're copying elements over. And so we're going to be using a lot more space than just the initial starting array. There are implementations of merge sort, like block sort, that are in place, but a lot of them either have trouble parallelizing or you sacrifice stability. Merge sort is also a stable sort, which means that these elements that compare equally will remain after sorting in the same relative position as they did in the beginning. So here's a little demonstration showing that merge sort is stable. So if we have two equal elements, 9A and 9B here, and we split up this list once and then twice, we have our single element lists, and then we want to recombine. When we recombine, 9A and 9B are going to just recombine in the same order that they were. And then when we add these two lists together, or these two arrays together, we're going to just put 9A and 9B at the end here, and they still are in the same order. So let's talk about runtime. Merge sort runs in theta of n log n time in the worst and best case, and in the practice case. So basically, if you are running merge sort, you can expect to get a consistent n log n runtime. However, as we'll see when we talk about quicksort, the constant factors for merge sort are fairly worse, and so in practice we might actually get, while it's the same asymptotic class, we might get different actual times for the running of our merge sort. And that's going to be it for merge sort. I think the big picture is just that merge sort is a very reliable, well-behaved algorithm that can be used to sort as long as you don't really care about the space complexity. Thanks, everyone.